Just one time I want to get it right. And I think I did. So of course there's nobody on the WebEx. That's how ironic. The one time I get it correct. And we're ready to get started. Okay, we have an exam next week. We'll start class off with about a 60-minute. My guess is it's not going to take nearly that long. My proposal is as follows. We're going to go over a homework today together in class. And if you turn it in, you'll get, I'm not going to waste time grading it because I assume that I'm giving you the right answers. So it's like an automatic 100. If we do that, I will give you some more problems to work on the weekend to prepare for the exam. And you turn that in on before the test, maybe that afternoon when you walk in, whenever you guys want. But I need to set probably a Sunday deadline because I need to give the solutions for it. So you guys will have the solutions. And if you'll let me do that, if you'll let me cover the stuff we need with homeworks, then I'll make the test easy. It'll take just a little bit of time. What I'm really interested in for the tests is that you understand the concepts. I don't care about drawing pictures perfectly or getting even the math exactly right. What I'm much more interested in is when you're faced with a question, do you know what formula to use? Do you know how to go about tackling the problem? So my job is to make sure you do. So we've looked at, for example, last time we looked at how signals propagate and what collisions are. It's fair game to have a question on that, even though we haven't had a homework question on it yet. You will. All right, does that sound all right? Okay, so my goal is nobody cries in the car on the way home and no divorces. That's actually something a boss taught me years ago. This will make more sense when you're older, but he said, I don't want anybody crying in their car on the way home, and I don't want anybody getting divorced over the job. So he said, if I make sure I manage where that never happens, I never cause that, I at least meet some minimum standard as a human being, as a boss. So we loved him because we thought that was fine with us, right? Okay, we're going to spend some time today going over one of the interactive animations. And we're going to dig deep into Wi-Fi. And I told you we would last time. So we are going to work through some problems together as we do this. And you can jot down answers for these as you go along. Type them up if you want. I will give you a document to actually answer them on. And you can turn your answers in on that. But it's a good idea to kind of keep track of what's going on, because what I'll do is ask the questions as we go along, and then we'll answer them together, and that'll become one of the homework problems. So I've already got some, so we're not going to be starting from scratch. So let me see if I can find this here. Okay, so this is what it is, TC2022. Let me drop it in here. That is. Okay. Okay. So what I'll do is ask some questions here. Okay. Not that. That one was tricky. So we'll do all these together. You don't have to worry about trying to scribble this stuff down as I scroll past it, because the important thing is that you understand how to get the answer. I'll give you the answer. I want you guys to know how to get it yourselves. Okay, 3. So this is what we'll work through today. There's that one. There's this. That. I just hope I don't overwrite this file when I'm done doing this. That would super suck. Okay. All right. Let's make this with alpha solutions. Okay, I think I have what we need. We'll go through some live because I will never be able to reproduce these exact images, but we'll go over these images to figure out how to answer the questions. Okay, first let me show you what are we talking about. In Chapter 7, they have more detail on Wi-Fi, but now's the time for us to learn it because we're looking at the flow chart in this chapter. So they're already presenting it. So this is a simulation from the textbook you used last year. My guess is you may never have gotten to this simulation. Do you guys recognize this? Did you use it? Anybody recognize it? Okay, so it's new for everyone. Right, that's what I expected. It usually is. So what this does is deadly accurately show you exactly what's going on, in this case between 3 hosts that are trying to connect to Wi-Fi. And it's a live animation, so I can do things like start it up and cause packets to get sent and see what's happening between the devices, and we're going to understand exactly what's going on. Because it's not that hard and it's pretty cool. So you'll need to be interactive or you won't grasp it because there's not a section in the book to go read and learn this. This is going to be something we'll learn together live. You can play with the animation, it's freely available, and that's something you might want to do over the weekend. So remember when we talked last time, we drew some interesting images of circles, and I was showing off my new circle ability with this drawing program I was so very proud of. And then if I recall, I think it was this class where I couldn't figure out how to turn the circles off. So the whole thing kind of turned to cramp on me pretty quick. All right, so let's say we have a Wi-Fi hotspot, and let's say this is the face of a clock from noon to midnight. Give me the time of day, roughly what hour you would like to see me drop another host on this Wi-Fi network. Somebody just pick a time. 7 p.m. or 7 a.m., I guess. And do you want it to be close, middle, or far? Let's pick one out close to the edge. All right? So I'm going to draw another circle for this one. And I need to make it about the same size as the first circle because they're both using the same technology. Does that look like the right place to drop the circle? Or should it be like this? Or should it be like this? The first one? Okay, why? Yeah, you must be, the Wi-Fi access point must be in your range or you can't connect to it. So we know the red dot needs to be in the circle we're about to create. All right, that makes sense. And why isn't it like much larger or something? Because it shouldn't be any different size than the red one. It certainly shouldn't be any bigger than the red one. Maybe it could be a little smaller. But what this guarantees is that each device is in the range of the other. So they can communicate to each other. They're within each other's Wi-Fi range, but just barely. So the signal they receive from the other party is going to be really, really weak when they get it there. So if they're talking at the time it arrives, they'll never hear you. It'll be like if I'm singing on stage at the Palacio de Bellas Artes, I'm never going to hear a mosquito buzzing around. But if I'm home, I'll hear it. So it's a difference in level. That's going to make a big difference in this simulation. Okay, give me another time of day to draw a third one, maybe in a very different spot. Okay, how about, let's see, let's pick this color. Does that look okay, like right about here? You want it out at the edge, or do you want it closer, or what do you, a little closer? How about like that? Is that okay? All right, so let's draw a circle for that one. And that looks like maybe like that. Does that seem reasonable? So the access point and the green one, they are going to get a stronger signal from each other. They're still in each other's range, but green cannot hear blue, can he? How do you know that? It can get to the center, but green is not in blue circle. That's how I know green cannot hear blue. And blue cannot hear green, although it sounds redundant. It's worth pointing out. Blue cannot hear green because blue is not in green circle. So not all of these combinations will always be true, but we're going to use this diagram, and we're going to talk about sort of what happens. But first, we need to make it a little simpler. Let's start with something a little easier and work our way today up to this. So what I'm going to do is go back, and we're going to be all nice and happy-like. And we're going to have one here, and we're going to have one here. Whoops, too big. Like that maybe, and then we're going to have one here. Everyone can hear everyone. They're all in this Venn diagram in the middle. So anything someone does, the other one should be able to hear it. Now for this simulator, we actually add a fourth device because there are three phones and one hotspot. I could, I guess, if I insist, we could add one more, but it starts to run the risk of making the diagram a little tough to see. But this is when we're in close quarters. This would be like in your room at home. All your devices can see each other. All right, I need to make sure I pull up Wireshark so I do not forget to use it. All right, so the first simulator we're going to have is said to be without hidden terminals. What that means is everyone can see everyone else. No one's outside of anyone's range. So I'm going to start the simulator. Everybody sees that the network is free. So there's a little legend down at the bottom that tells us what the colors mean, but we'll spend lots of time going over that. And all I have to do to transmit a frame is to click on one of the station names. So I just clicked on the word station 1. So let's see what's going on here. And in order to figure out what's happening, we are going to try to open up our flow chart from our textbook and grab what's happening. I think that's one layer off of where I want to be. I may want here. Yeah, this is the one I want. So we're going to find the Wi-Fi one. It should be right here. Bingo. Ha! Look at that. I nailed it. Okay, I have no idea what slide number that is. It looks like it's in the middle. The middle would be right about here. Yeah, right here. Yes? It's not. Thank you. Thank you, thank you, thank you. I got the microphone. I was doing so well. Okay, thank you. All right, so this is the flow chart that we want to use. And to go back to the diagram again, we're going to use the simulator where all three of the phones are within range of each other and the access point. They have to be in range of the access point or they can't join the network. But they also are all in range of each other. And the diagram that we drew to go along with this was this. The red one in the middle was the access point. Turn off, circle. And the rest of them are numbers 1, 2, and 3. So they're all within range of each other. Okay, so what we did was we started this up. We started it running. I can do it again. And I clicked on station 1, and it began to send a packet. And then it goes back to idle. So what does the flow chart say is supposed to be going on? I have something to send. Is the channel free? I wait a little bit of time, and I send a request to send message. So let's see if we can follow that so far. I have something to send. I wait till the network's free. That's good. And I wait a little bit extra time. I can't tell that. It's just all looks like green to me. And now I'm going to send a request to send message. Blue means RTS, request to send. When I do that, the network becomes busy. I believe that because I'm making it busy myself. All right, who else sees that the network is being used when I send this request to send packet? Stations 2 and 3 also turn red, which means that the transport medium is busy, or the media is busy. So they can both see that I'm sending a message to the access point. They're close enough they can hear it. And they're also quiet right now. They're not talking. So they can especially hear it. So that's good. Because they hear me making the request, they know when they see the whole request make it onto the wire, they enter into this mode of silence for a while. They assume that I've got the network. It's going to be mine for a little bit. No point in them trying to do anything. So they're going to stay here and they're going to listen for the ACK that's going to come at the end. All right, so I've sent my request to send. There's another little space after that. Wait a little sifts. Did a clear to send message arrive before my timer went off? Well, I don't know. What's the next thing that happened on this timeline? This down here looks like the next thing as I go from right to left. So what is this? This is a clear to send message, and it's coming from the access point. All right, perfect. So I receive that message. I see the network's busy, and apparently I interpret it correctly because I begin to send my data. That's what's going on with this brown is I'm sending my data frame. When I'm done, I wait a little moment because this says you send the frame. When you're done, you set a little timer. Do you get an ACK before the timer goes off? If yes, success. So I wait a little bit. Do I get an ACK? I sure do. Here's the ACK. Everybody else hears it as well. And they all go back to believing the network is free. So far, so good, right? All right, so let's see what happens when 2 sends something. Does it look any different? Should be exactly, and it looks the same at first glance, right? Same thing with 3, if I send something with 3. But of course, that's not interesting enough. What's more interesting is if 2 people try to send something at the same time. So here's what I'm going to do. I'm going to click on Station 1 and Station 2 quickly. All right? Click, click. And we'll pause. Station 1 starts off the same way. He has something to send. He requests permission. He gets permission. He begins to send it. I can pretty much promise you that somewhere right around in here is when I clicked on Station 2. So Station 2 sees that the network's busy. He's in nav mode. And when the network is available again, when the ACK is given to Station 1, the network is free. What's this gray box? It's a countdown timer. What do you suppose that's for? Exactly. So let's try it again. I'm going to go 1, 2. Notice anything different? Let me try it again. 1, 2. How about now? You see anything different? What is it? It's not your imagination. They're changing sizes. All right, we can try it again. 1, I don't want to do that. 1, 2. It's really bigger now. It doesn't just get bigger, I promise. There's little ones, there's even zeros that show up. So what's happening is I'm seeing that the network is available again, but I'm waiting a random amount of time. Why would I do that? That's exactly why. How did you know that fast? Were you thinking about Ethernet? Yeah, on Ethernet we used random numbers. So exactly, why not? So why do I need a random number here? I mean, why don't I just start sending when the network's free again? Why did Ethernet roll random numbers when the network was free again? So remember, this is Wi-Fi. So one key difference with Wi-Fi is I can't count on detecting collisions. It's not a CSMA-CD network for collision detection. It's a CSMA-CA network for collision avoidance. It says right here, CA, collision avoidance. So you should not assume that you can ever hear a collision. Just always make that assumption. And you need to figure out, if that's always the case, what should I do? Does it change what I would do? Does it change anything? Like the fact that I can't see a collision, how's it going to make me act differently? And they figured out a way for it to work. So we'll continue on. All right, the reason why there's a random back off here is because two things happened. Number one, I had something to send in my queue. I was waiting to send something, and the network was busy when I tried. Both things have to be true. You'll notice number one has no gray box. He shows up on the network. He gets something to send. The network's not busy, so he just sends it. Network 2 shows up. Because I clicked while 1 was sending, he has something to send, but the network was busy. So there may be lots of people in this situation with us. Maybe 2, 3, 4, 5, and 6 all have something to send, and they all notice the network is busy. So what you don't want to have happen is as soon as the network's free again, everybody dogpiles on the network. Because you'll just have collisions that you can't even detect. So nothing will happen. Nothing good will happen. Yes? Because if everybody picks the same number, then everybody will start at the same time. And they'll all transmit on top of each other. So because I don't know if there's anyone else who needs to send, the safe thing to do is to wait a random time and then go. And knowing that everyone else who has something to send is also waiting a random amount of time. So we will probably be spread out. We probably won't try to transmit on top of each other. But this gets really bad when we look at the other simulator later. This one's the easy one. So it gets confusing. So we'll start with this one and get all the basics down. All right, so he waits a random amount of time. The network remains busy throughout. He's listening. He's not sending anything. Now, you could be unlucky. You could be waiting here like a good packet, waiting for your turn. And station 3 wakes up for the first time, shows up, has a packet to send, looks at the network right here. It's free and starts sending. And you're like, God, just got right on top of me. I was next. You're supposed to wait your turn. But how does it know who's got something to send? So if it's certainly possible that while you're trying to be nice and spread out, some klutz shows up and starts transmitting in the middle of the free window. Perfectly legitimate. Happens all the time. Can't do anything about it. So the rule is you roll a random number, you listen. If it remains free for that entire time, then you send your request to send. Hopefully you will get a clear to send back. You send your data and it's acknowledged. So far, so good. Okay, let's make it even more. Ready for level 3? Okay. 1, 2, 3. All right, so we're going to stop. 1 sent first, that's for sure. After 1 was done and the network was free again, 2 and 3 both rolled a random number. Who rolled the smaller one? 2. You know that because when 2's timer went off, he started transmitting. When he did that, 3 sees that the network is no longer free. He stops. He's like, missed my chance. He literally did miss his chance. So he sees the network is free. He goes into nav mode again, like this again. So he's going to wait, and when the network is free again, he'll roll a random amount of time. No one else is going to compete with him. So at the end of this random time, it's all his. Now he's finally able to send a request to send, gets the clear to send, sends the data, gets an acknowledgement. But that doesn't always happen that way. So I'm going to go click again. 1, 2, 3. Same thing happened that time. We'll do it again. We'll let it finish. 1, 2, 3. Look what happened this time. This time 1 got to send his thing when the network became busy. This time 3's random number was smaller, wasn't it? So he got to send his packet first. And then 2 rolled another random number and he got to send. So these guys do not assume they can see other people on the network. If they happen to get lucky and hear that the network is busy, they will back off and go into nav mode. The problems come up when they can't hear the other people. That's when the problems start happening. That's when it gets ugly. So again, one way you can tell this is a no hidden terminals problem is when one of the stations starts sending, the other stations can see it. You know when you see that it's this picture. One of them starts sending and the other 2 can see it. They are all in this one's circle. And because they're all in the AP circle, they're all in the same polygon. That's proof. And so that's how you'll spot that, is you see. So this is what it looks like. So let me see if I can ask a few questions about this. Yes? Wi-Fi always works with collision avoidance. Because you can't hear, you can't always detect it. You can't always hear what's going on. You can't always hear the other side. So if you're on the other side of the hotspot, like down at Food Box, the access point may be able to see you through the glass, but I probably cannot. And I can prove that to you in a minute. We're going to use Wireshark and I'll show it to you. It's really cool, actually. It's amazing the stuff you can learn from just Wireshark when it's not even telling you what people are doing, really. Okay, so let me see if we can ask some questions about this. You will get these questions in writing. The problem is I can't reproduce exactly the image. So what I'm going to do is paste it into a layer so at least it's bigger. No, not that. Okay, so here's our diagram, and here are our questions. Who has, on this picture, who has successfully sent data? Stations 1 and 2, and that's it, right? Okay, that's the answer for the first one. I will give you this question. You can answer it later if it's obvious to you, or you can jot it down now if you want. I probably should number these stupid things as well, don't you think? That would be kind of nice. You know, I wrote this on the fly as I was taking screen dumps yesterday because we just did it together as a group. So let me, let's do these A, B, C, that kind of thing. How about that? That looks okay, doesn't it? So who has successfully sent data? 1 and 2, you said, right? Okay, let's look at the next question. Does 3 have something to send? How do you know? Do you guys agree with that? 3 has something to send because he says it's sent a request to send. He must have something to send. He's also got a random number thing. That's another dead giveaway. Even if all you saw was the gray box, you could still make the same conclusion. Because the gray box shows up when 2 things are true. You have something to send, and the network was busy when you tried. So right there, you know you had something to send. Okay, why did it enter random backoff mode? What 2 conditions were true? Well, we just said them, right? We just told them. What are they? You have something to send, and the network was busy when you tried, when you first looked. All right? So station 1 sent 2 different data packets. So I must have clicked on him twice. How many attempts did it require for him to send his 2 packets? 1 each, 2 total. Okay, I like that answer. What about station 2? So how many packets does 2 have to send? Look all the way to the end, make sure you think so. So what does that gray bar mean? He has something to send. Remember? So if you gave me the answer, how many tries did 2 require? We really don't know how many packets 2 has to send. There's at least one more, but maybe there's more. And how many tries do we see so far for station 2? We saw 2 tries for the first one and 1 try for the second packet. So what's the answer? How many tries does station 2 require? Exactly. Say it again. At least 3. Greater than or equal to 3. You see why that's the answer? I took 2 tries. On the second try, I successfully sent my first packet, and I got an acknowledgement. But I went back into random backoff mode again. Why would I do that? Because I still have something else to send. I'd only go into random backoff mode if I have something to send and the network was busy when I tried. So I also know 3 still has something to send, but this poor guy has never sent anything yet. He's still trying to get his first packet out the door. Poor bastard. Okay. So the 2 conditions are, well, let's go back and look. You have something to send, so the station has to have something to send or you will not enter this flow sheet. So the application, or in this case, the IP layer, because it's the next layer up, the network layer has sent you an Ethernet frame that wants you to, or payload that it wants you to send over Wi-Fi. And the other thing is the channel is not free. So the channel is false, so you're going to go back and wait. What this diagram does not show is that there's a random backoff in here. The diagram's not perfect, but it needs a random backoff in here. But at least it's gray, so it's kind of a hint. You entered this gray mode, so okay, well, at least it's gray. So that helps me remember what's going on. So if I come back over, I entered the gray mode, I had something, the network was busy. Probably I got my packet to send over here. And so once it became free, I tried rolling a random number. Somebody else rolled a smaller one. The network was busy again. I saw them send something. I went back into nav mode. When it became free again, I rolled a different random number. This time I won. I got to send my stuff, and I'm finished on that one. But if we go over to our diagram, ours is a slightly bit more complicated. It took me 2 tries to send it, but I still have a packet left at the end. I'm still in gray mode, so I know I still have something to send. I'm not finished. I wouldn't be in the gray box if I was finished. I'd be doing nothing. Okay, so back to the question then. How many tries does station 2 greater than or equal to 3? Well done. Okay, 3 acts are shown. In order, who are they for? Okay. Okay, are the first 2 for the same packet? And so which packets? It's got more than one, right? So I think what you're saying is this is the act for station 1's first packet. This is the act for station 1's second packet. This is the act for station 2's first packet. That make sense? So that's the detail you want. Right? So first 2 are for one packet each, and then the second. But for different packets. The first one is for station 1's first packet. The second one is for station 1, but it's second packet, packet number 2. You just look to what's closest. Which data packet just finished when you sent the ACK. That's how you can tell. Okay, we're very lucky with this simulator because everyone can hear everyone, so no one's going to step on anyone's toes. You can get crazy results if you really try. So if I do a bunch of these, sometimes I'll just get insanely lucky, and we'll have two people send at exactly the same time. So I'm going to do that. And you can see I have a big queue of packets over here. Bingo. Look what happened right here. Packet 2 was sending a packet. Everybody has lots of packets left to send. The queue is big for each person. So I send the packet, I finish, I get my acknowledgement, the network is free. All three roll a random number. And the first two roll the same random number. Why not? It's random. It can happen. At the end of that random period, what happens? Right here. They both send them at the same time. Which one does the access point receive? Does it receive a correctly formatted request to send packet at all? No. It receives garbage. One of the reasons why it receives garbage is because it's listening and not talking. Remember the difference between rolling the piece of bubble gum and blowing the big bubble? Who gets more gum? Right? So the signal is very weak. Even if you're in the same polygon, it's still much, much weaker when it arrives wherever it's going than when you sent it. So because the access point is silent, he can hear the garbage arrive. But if he had been talking at the same time, he would never have heard it. It would be much louder what he's saying, and it would just be background noise. It would be Juan Gabriel singing at Palacio with the mosquitoes, but you'll never hear it. He's too loud. Okay? Hope nobody's offended by me using a Juan Gabriel. He's kind of a big thing in Texas, so people know him. Yeah, whatever. All right, so two people send at the same time. The access point heard neither one. How do you know that? What should he have sent back? Yeah, should send back a CTS. Let's go see what the flowchart says. I send my RTS, I set a timer. Is it received before the timeout? So there's a timeout. Timeout's apparently pretty long. And if I didn't get it, I'm going to back off again. So let's see if we can see that happening. The access point never got anything, so he never sent anything. And I'm waiting, and I'm waiting, and I'm waiting. What happens while I'm waiting? Station 3 sees the network is free again. He waits a little extra time. Plenty of time for the access point to send this if he wanted to. But that's why you have that little extra wait. You don't start sending the instant you see it. You wait a little bit. The access point may be about to respond. And you wait a small random time. You're lucky because this random time that you're waiting is still within the timer for these guys. They're still holding out hope they're going to get a clear to send. It's never going to show up. If that timer went off, they would send it again. But they're waiting. They waited so long, and this number was so small that 3 was able to kind of slip in. Roll a random number. Why did he roll a random number? Because when he tried to send, the network was busy. He had something to send, and the network became busy again, right here. So he just does it again. And this time he sends it. No one else is talking. These guys go back into nav mode, and they're like, you got to be kidding me. I send my request to send. I don't get a clear to send. Somebody else sends a request to send. So now I have to wait. So they go back into nav mode because they can see it's busy. They can see that it's busy because he's going to get his clear to send, and he's going to be happy. He's going to continue on. So you can have things, even when everyone can hear each other, you can still have conflict. That's really important to remember. Right? This is like the only example of it. This is when two people try to send a clear to send at the same time. They will never try to send data at the same time. Why? Why will two? So here we see a conflict. 1 and 2 tried to send a request to send at the same time. And my claim is you will never see them send data at the same time. Why not? What does it take to send data at the same time? What does it mean happened? You got permission. What's permission? CDS, clear to send. How many is the access point going to send at one time? One. Only one person gets permission. How can two people get permission? It's impossible. It sends it to one party. So you can never have clear to send going to more than one person, and you can never have data be said, this is it. This is the one and only chance you've got. Now, when we look at the ones where there's hidden terminals, everything can happen. It's like a car wreck. Acknowledgements can conflict with each other. Everything will happen. All right, so let's make sure we get the questions done here. We have a different diagram now. It may be what we just did. Let's see if we can figure it out. All right. So here's another example. We had something in the queue to send. Okay, who had something to send at the beginning of this exercise? So let me label these again. Okay, I really wanted that to be H. Thank you very little. Awesome. Let's do it the hard way. Really? Oh, there may be a spurious gap. That's what's going on. Okay, let's try this. Bingo. All right. So we'll do this. I, J, K, L. What else I got? M, N, edit, here, here. This is quite long. Didn't like that. Try the whole paragraph. Okay. So we are back up at H. In this picture on the left, who had something to send? Station 1 did for sure. Station 2 did. Did Station 3? So at the beginning, they all three had something to send. So this is not the beginning of a trace. I apparently took a snapshot of this after it had been running for a while. All right, I agree with that. That sounds like a decent answer. So that's the answer for H. Who has the smaller random number? So these three all rolled a random number. Who rolled the smaller one? So it's tied. It's an empate. 1 and 2 both had the same random number. We just saw that happen, didn't we? Okay, so it can happen. So 1 and 2 have the smaller random number. All right. We know that 3 did not roll the same random number. How do we know that? How do we know 3 didn't roll the same random number as 1 and 2? He stopped when he saw the network was busy. He must have not been ready to send something himself. So his random number was actually bigger than the other two. Right? And because he can hear the other stations, as soon as they start sending this, he hears that the network's busy. He doesn't know with what. He doesn't care with what. He just sees that there's activity on the network, and so he stops. He'll wait until it's free, and then he'll try it again. That's the way the rule works. So this is exactly like the one I just showed you. Both guys send it. They both are waiting for a clear to send. It's never going to arrive. The third guy slips in and gets his thing done, and they're like, ah. In fact, it's even worse because he has another packet to send. He wins again. He wins over here. These guys can't catch a break. And they finally, get stuff done over here. Okay, which RTS does the access point choose to respond to? It was this one, Station 3. Why did he choose to respond to 3 and not 1 and 2? There's several answers for that. Give me a couple of good answers. Why did the access point choose Station 3? So at the time he responded, what were the other guys doing? And this, they'd already sent their RTS, but they're waiting for a response. What does the access point think they were doing? Yeah, but what did the access point get from them? Or garbage. He didn't get a clear to send. So they think they've sent it to the access point. Why can't they hear that they've collided with each other? That's exactly why. They can't hear each other. They're in the same circle. They're not that far apart, but it's the bubble gum instead of rolling the piece of gum. They blew a bubble. So the signal strength, even with very little distance, is a tiny fraction of the sending strength. So they're both talking. You know, my Aunt Ruth used to tell her kids, God gave you twice as many ears as he gave you mouths because he wants you to listen more than talk. It's a good one, isn't it? Do you guys have that in Spanish? A version of that? I'm sure you did. I'm sure you had something parallel and similar. But these guys are both talking at the same time, so they can't hear what anybody else is doing. So that one's kind of interesting. The access point can't really tell what's going on.
But if they were able to hear each other, they could sort it out and
if you could guarantee they could hear each other, you could implement a protocol that would negotiate directly one with the other, or not bother waiting for the clear to send because you know it's never going to come. Just stop and immediately try rolling another random number and sending the request again.
No, they would go gray again.
Yeah, they would just not wait all this time. Right now they're in a big long timeout waiting for a clear to send to show up. It's never going to make it. They don't know that because they didn't know there was a collision. If they knew there was a collision, they wouldn't wait for something because they know it's never going to get there. So they would just start sending. They would roll another random number and send another request to send. That's probably what they would do. Okay, so one reason was, the answer was, why did the access point choose station 3? And my answer, one answer I can add, there's lots of right ones. One of them is, it's the only request it ever saw. It's the first one it saw. These things aren't request to sends by the time they get to the access point. It's garbage. So he responded to this one because it's the only valid one he received. You could also say he received this one because the other two collided with each other. But the access point doesn't have to figure this out. He doesn't care whether it was a collision or somebody turned on their microwave oven, which uses the same frequency range, by the way, or what's going on. It could be a conflict with somebody on another Wi-Fi hotspot. We all use the same frequencies. They can interfere with you too. So who knows why, but he doesn't have to care. He's always going to do the same thing. Ignore it. If he didn't get a valid packet, he'll ignore it. So it's the other guy's responsibility to resend again. He can't send something back saying, I'm sorry, I didn't get that. What was that? Because he doesn't know who sent it. It's garbage. How can he know what's happening? Okay, why didn't 3 go into nav mode when he saw these two packets get transmitted? Why, every other time 3 sees something, he goes into nav mode like a scared cat. Why didn't he enter nav mode now? The network appeared to be busy. Why not go into nav mode? So let's look. Does he wait for this acknowledgement before he goes into nav mode down here? Here's a request to send, and he goes into busy and instantly goes into nav mode. Before the clear to send shows up, when does he go into nav mode? At the end of the request. Why does he wait until the end of the request? He goes from thinking the network is just busy to deciding he needs to go into nav mode. What happened at the end of this red bar? What has finished at this point? If I draw a line, the line will go right from here, right down. So the beginning of his nav mode corresponds with the end of the request to send. So what's going on? And over here, this request to send ends here. It's also red, but he did not enter nav mode on this one. He did enter nav mode on this one. So it's not enough just to see that the network's busy. That's not sufficient because over here the network was busy and he didn't do it. He didn't enter nav mode. And it's not because the access point responded because he hasn't responded yet. There's still some space here. So tell me what's going on. What's station 3 doing? How does he decide on that first time not to go into nav mode, but the second time around he does? It got garbage, so it never got an RTS. It doesn't know what happened, but it wasn't an RTS. And on station 3, he was able to get an RTS. On the last one, on to the left, when he did enter nav mode, this one wasn't in conflict with anybody, right? So he heard it clearly, and he entered nav mode because he's now able to tell what's going on. Yeah, and he said, that's good enough for me. I know that means the network's going to get used. So I will go into nav mode. So it must be, the flowchart doesn't tell us, but it must be because he received a unmistakable sign that the network is now occupied. It's just a shoe-in. Someone's going to get it. That's what he believes. Whether the access point actually responds, nobody knows, but that's good enough for station 3. It's kind of interesting. It's pretty conservative. He's being pretty conservative. So 3 didn't go into nav mode because he never got a request to send. He never saw anything that would cause him to. Why would he have entered nav mode? Yeah, so what happens if he can't even hear the station, even if he's listening and no one else is talking and there's no collision, it's just too far away and he can't hear it at all? What's going to happen then? We'll have to look at the other simulator in a minute to answer that. You'll see exactly what happens. Okay? All right. Zooming in. I'm zooming in right here at the front, right over here. Who has something to send at the time of the arrow? So let me try to erase some of this stuff if I can. Okay, at the time of this arrow, it's basically right here, at the beginning of the gray. Who still has stuff in queue? Who's waiting to send a packet? Well, 3 has something to send, obviously, or he wouldn't be rolling a random number. Who else has something to send? Yeah, they still have something to send. There's lots of signs. They tried sending a request. They went into nav mode and immediately came out and rolled a random number. They're only going to do this if they have something to send. And so everybody does. All right, that one's an easy one. So why didn't 1 and 2 show they're in a random time interval? So these guys, all 3 were in a random time interval, but now only one of them is in a random time interval. Why are the other 2 not in a random time interval? Why are 1 and 2 not showing a gray box up here? Yeah, they're in a timeout. They're waiting on a CTS, so they're not going to enter random mode. They're in a different timer. They're in this CTS wait time. All right, so remember, all this is happening at layer 2. None of this is IP, none of this is TCP, none of this is windowing, none of this is wired exponential backoff. This is just Wi-Fi. The chapter we're in the book is only up to layer 2. Yes. Yeah, so the last question is basically, we started off a minute ago, all 3 were in random backoff mode. Something happened. They all three still have something to send. Nobody got to send their data. I didn't see any data get sent. We wait a moment, and now 3 enters this random back-off mode again, but 1 and 2 do not. Why didn't they go back into random back-off mode again? And the answer was because they're waiting on a CTS that's never going to arrive. They don't know that. They're waiting on a clear to send. 3, why isn't 3 waiting on a clear to send? Why was 3 able to do this gray bar? Why wasn't 3 also in the same position as these guys? Why wasn't he waiting on a clear to send? And he's not in that mode yet, not until the far left. You didn't see any? That's part of it. He didn't enter nav mode because of that, so those two are related answers. You need both of those things to be true. He never sent a request to send. Why would he be waiting on a clear to send? He never sent an RTS. There's no reason to wait on something if you're not expecting it. So he never got to send his. He got cut off early because he rolled a bigger random number. These guys rolled a small one, and the problem is they rolled the same one. But for 3, 3 just said, I tried, the network got busy, so I waited and I tried again. So now I'm waiting on a clear to send. Okay. You ready to switch over to the other one, or do you want a break? The next one's harder. You want a break, or you want to keep going? Keep going? Is that what you guys want to do? Yeah, you want to, I don't care. That's fine. I told you guys to bring food, and that's perfectly fine. Absolutely. So you need to go grab it, right? So let's take 5 minutes. Let him go. This is too long. I mean, my schedule starts off at 8:30 in the morning with a departmental meeting, and then I have a class from 10 to 1, and then I have class from 4 to 9. So I had meetings from 1 to 2, so I had like 1 hour. I went directly to Centrales immediately. My ride dropped me off at 8:31 this morning for an 8:30 meeting. Very late. So usually by the end of this evening, I'm ready to eat my hand. So we'll wait. Yeah, nothing's going to be open when we get out of class. So let me turn this into a homework while we're waiting. Let's just finish it up. I'm going to pause the recording for a minute. Okay, so with hidden terminals is different. With hidden terminals, we're not going to be able to see what's going on. A motion station can hear the access point, but it cannot hear any of the other stations. That's basically what's going on. I think they're walking in the door. Let me mute it real quick. Okay. Back to sharing again. Okay, so let's take a look at what's going on in this one. I'm going to reset and start over. I'll make it a little bigger so we can see it. And when station 1 starts off, do you notice anything different? There is something important different. Perfect timing. Welcome back. You were right. You won. Yeah. Yeah, you got it. Okay, so is there something different on this hidden terminal exercise? 1, 2, and 3 cannot see each other. They all can see the access point, and the access point, of course, can see them, but none of them can see each other. So how do we know that from just looking at this diagram? They'd only do that if they had something to send, right? That's true. They don't have a random number, so we know they don't have something to send. They didn't see that the network was busy when 1 sent the RTS. Do you see that? They still think the network is green. So they've seen nothing that would cause them to go into nav mode. When do they see something that lets them go into nav mode? First of all, when do they see that the network's busy? When the access point starts talking and the CTS is sent. Once they receive a valid CTS, then they can go into nav mode. They won't go into it for as long, but they'll at least enter nav mode. So that's how you can tell they can't see each other. Right at the very beginning, just look who sees that the network's busy when someone else is talking. You know they're all three in range of the access point because all three go busy when the access point talks. And we know this was successfully received by the access point because he responded. Right? So far, so good. So let's try again. 1, 2. Good Lord. What a train wreck. So all I did was click on 1 and 2. So what's going on? This is a really interesting one. This is harder than the homework. But let's talk through this. So somebody start to walk me through here. What's going on? I'm going to point at things. What's happening here? Okay, and does the access point receive it? Yes. How do you know? Because it responds with the clear to send. What else happens while he's sending the clear to send? Very unluckily, Station 2, who never heard the request to send and therefore did not enter nav mode, picks the worst possible time to try to start sending a packet. And the network was not busy. He did not believe it was busy when he was asked to send it, so he doesn't have a gray bar. So he just starts sending. He sees it's free. He would have heard the access point in a moment, but they basically started sending at the same time. So, one's waiting on a request to send. By some miracle that I'm not sure I understand, he gets it. I don't think that's possible. I think what would have happened is one would have received garbage because two people were talking at the same time. But depending on where 2 was, if he was on the other side of the Wi-Fi hotspot and the access point was much closer, then go for it. Station 1 would have received it, and he would start sending. Okay? So 2's really behind. He doesn't know that 1 asked for a request. He doesn't know the access point said it was okay. And now he doesn't know that 1's starting to send data. He is clueless what's going on. So he doesn't get an answer back for his own request to send because he's waiting on 1. So this is how long that timeout is we were wondering about. He figures there was a collision. He doesn't see the network busy, but he still goes into this gray mode because something went wrong. He knows he didn't get his permission back, the CTS back. So he waits a random amount of time. Meanwhile, Station 3 has seen everything happen. He's in nav mode as a courtesy to Station 1. He saw the access point send the clear to send, and he goes into nav mode. 2 never saw any of that. He is like stumbling ahead. This is real. This happens all the time. So he waits. He tries to send something again. He finishes, wouldn't you know it, right when this guy finishes as well. So he's clobbering on top of the end of his data packet. These things overlap. So the access point never received the whole data, and he never acknowledged it as a result. Because this knucklehead started sending another request to send while this guy was still sending data. Because he can't hear him. And he never heard this, so he never entered nav mode. So he just, woke up and started sending stuff. So he ruined it for 1. We've accomplished so far exactly nothing on this network. We've sent a lot of stuff around. Nothing productive has happened. So he waits. His request to send does not get a clear to send. Why not? Why doesn't he get a clear to send for this? Yeah, the access point heard most of a data packet from 1 and got some garbage, which was the beginning of the request to send. 2's request to send, the last part of it showed up okay, but the first part of it was garbage because of 1's data. They conflict with each other. So the access point never got the data and never got the request because they overlapped with each other. And so he didn't respond. He waits again. This time, 1 rolls a short number, asks for something, gets the response. He's not talking, so both of them see the response, and they both enter nav mode. Now we're cooking. So 1 can send the data. He will get the acknowledgement back. Everybody sees it's over, and they both will continue on. I don't know if 3 has nothing left to send. Yes. Correct. So, and vice versa. Yes. Yep. So the access point, this is the same packet when I send again? Yeah, that's what this one is. It's the same packet. It's a resend. He never got the acknowledgement. That's a great point. Thanks for asking that. Yeah, this is a resend of the same packet. Wi-Fi doesn't care. It doesn't care what you're sending. It's just as another packet to it. But we can look at it and we know it's a resend, or, you know, we'd have to read the standard to figure out if it really will resend. We may just give up and let the higher level figure out what it wants to do about it. IP won't want to do anything about it. TCP will, but IP won't. But it's judicious. It's probably a good idea to guess that it's the Wi-Fi transmitter resending its own packet. It probably held on to a copy of it because Ethernet does that. Wired Ethernet also holds on to a copy of a frame, and if it detects a collision, it will resend the frame itself. That's how it does exponential backoff. It can't do exponential backoff and resend it if it doesn't have the frame. So if Wi-Fi is patterned after Ethernet, then my guess is you are right, it's a resend of the same packet. I'd have to go read the standard. Question?
Yeah, idea.
So what's happening now is none of these stations can hear each other. So the diagram is they're all in different circles. Do you remember when we drew our circles earlier? Now we're talking this one. Except there's a gray one in here, and if I'm going to be, correct, which is kind of nice to be, then I probably need to finish drawing this thing so that at least it's accurate. So how can I draw this? I'll have to draw it here. And where are my tools? Barra de R. Nobody's in anybody else's circle. Okay? So to go back and explain what that means when we can't see what's going on is not this one, not this one. Uh-oh. Where did it go? Nope. Nope. It was this one. No, it isn't. Where's the one with two things in it? It's here. Okay. All right, so what happened is one sent something, nobody else heard it. He conflicted, wrote on top of the clear to send. So one never got his clear to send. He shouldn't have, but the simulator says he did. It's possible, but I don't like it. So he starts sending, but he doesn't get to finish to send because this guy starts overwriting it again. Okay, here's proof this is wrong. Do you see the proof? It can't be close enough to interfere with his data, but too far away to interfere with his clear to send. They can't both be true. I probably could try to design something that would do that, but if this is strong enough to screw up him hearing this signal, this is strong enough to screw up him hearing this signal. They can't both be true. So this is a bug. Finally caught a bug. There's always a bug. Okay, but nobody can hear each other, so he's talking on top of the data. The data never gets acknowledged because he's corrupted the data. This guy tries again. He gets it out. He's finally able to send the data. Now this guy's going to try to send something. And so it's horrible when you can't hear the other stations. So let's finish the homework with a different image. And I want to show you Wireshark, and then we'll talk about the midterm. We'll talk about the exam a little bit. So let me switch over to this. We're going to pop this in. This is the image for the second part of the homework. And this is the same type of problem. This is with hidden terminals. People can't see each other. How can you tell by looking at this image just like that it's hidden terminals? Yeah, they don't hear it. They don't think the network's busy. They still are green. Okay, so what's the first thing you notice that's different? That would be it, what he just said. 2 and 3 can't hear 1's RTS. That's a short way of putting it. 2 and 3 cannot hear 1's RTS. What causes them to realize that the network is busy? The access point, CTS, everyone can see the access point. When the access point talks, everyone sees it. So it's the access point's transmission. All right, good. After 1's first successful transmission and acknowledgement, which is all right here, who still has data to send? I agree. Say it again. Everyone. And they all do it at the same time because they're all trying to do something at the same time right here. Okay, they all three have something to send. Why doesn't station 2 have a back off shown? In other words, why is there no gray bar here? So he had something to send, but the network was not busy when he tried. So he tried right there in that green box. Wow, what are the odds of that? He tried right there, and 1 and 3 never saw him do it because they can't hear him. So they went ahead and sent their stuff too. So why doesn't 2 get a clear to send back from sending that? He sent the RTS right here. Why doesn't he get a clear to send back? What do you guys think? Why doesn't the access point respond to this request to send? It's garbage again, right? Because it's sent at the same time 1 is sending something. The access point never gets either one of them. Okay, so even though 2 starts sending an RTS first, why do 1 and 3 continue to send 1 also? Even though 2 sends this blue, and why does 1 and 3 continue with their timer, send a request to send? Why do they keep going? Why don't they stop and enter nav mode? They can't see station 2. They can't hear anything. They think the network's still free. They don't know. That's why. Because they don't know any better. And why doesn't station 2 get a CTS? We just answered that. Because the RTS was never received. Once 3, down here, sends his RTS, why do 1 and 2 stop their countdown shortly afterwards? Like here's a countdown and here's a countdown. 3 sends his request to send. Why did these guys stop? Because the clear to send from the access point they heard. And so they stopped sending. Okay, if you have a huge number of packets to send, really, really big, 1 million packets, distributed evenly over a bunch of different stations, and at some point, one of the stations has M packets left in his allotment. So let's say it's 10 different stations, 1,000,000 different packets. Each of them have 100,000 packets to send. And we take a snapshot and we look at what's going on and we ask Station 1, how many do you still have left? And Station 1 says, pick a number, 30,000 left. How many would you expect the other stations would have left to send also? So the randomness, we would hope, would make this fair. That's what we're hoping. So the access point has to be a little careful because people who are closer, their packets get there first. They don't have to travel as far. So one of the reasons there are these short interframe spaces is to give a chance for the furthest station away to get a word in edgewise, as we say. They're going to be able to say something. So even though you think the network's free, wait a little bit. Somebody else may be using it. Be polite. The access point can enforce whatever queuing it wants. It can give priority. There was an announcement a couple of years ago between Phil, oh my God, I'm going to forget his name. Phil Cook, is that his name, the CEO of Apple? His name's not Phil. Tim Cook, thank you. And John Chambers at the time, who was the CEO of Cisco. And they agreed to trade information between wireless hotspots and Apple devices about the type of data that was being sent. So for the first time, Cisco's routers were going to actually look at the prioritization bits inside of Wi-Fi frames that Apple's software would set to let the router know if it was a FaceTime call or just an email or an audio clip or just a web page. Because in busy environments like public safety or airports especially, where the networks are generally saturated, you have no chance to have a decent call if you don't give priority to those packets. So they're not going to take over the network with it, but you know, that was significant. So that's an example of an access point setting whatever rules it wants. It can give prioritization. It can starve people out. Access points do things like hide themselves. They will never transmit a beacon. You will never see their SSID in your list. You can say join other network, and if you know what it is and you type it in, you will join it. But they will not advertise it because they don't want everybody hacking at it. Well, that's not very hard. Just open up Wireshark. Salud. Open up Wireshark and see which SSIDs people are connecting to that aren't sending beacons. That's pretty easy. Then you know. Then you can like knock away at it. All right, you can also restrict people from using the network. Their MAC address has to be in a list, or they do not get to connect to the hotspot. That's very common as well for administrative networks, for example. Okay, I want to show you something in Wireshark. So what I'm going to do is turn off Ethernet and turn on Wi-Fi, and it's going to cause me to drop my connection for a minute. So at some point, you guys are going to stop hearing and seeing me for 5 seconds. And it should be happening, not yet, not yet, not yet, yet. Okay, I should be back. So what I'm going to do is open up Wireshark, and I'm going to activate a mode that may not be available in all of yours, but if it is available, it's fun. So what I'm going to do is go to my capture menu, and I'm going to turn on monitor mode, which is available on my Wi-Fi interface. Right here, it's just a blue checkbox, monitor mode, and I'm going to close this up, and now I'm going to open Wi-Fi. I'm going to let it run for a little bit, and stop it. So what monitor mode does is a couple of things. It grabs everything it can, but it also stops trying to interpret higher level protocols. So you notice nowhere on here does it say this is TCP or UDP or HTTP or any of that. It just says it's 802.11. So it's just kind of showing me more raw data. But it's pretty cool because I can see some beacon frames coming from various hotspots. I can see at least 2. Here's a bad disassociation packet. that somebody sent. Here's a QoS data, another malform packet, a collision, a block acknowledgement, a request to send, a clear to send, another disassociation request, another request and clear. So I want to sort by the type of packet. So we have some Aruba networks around here as well. I didn't know that. Did you guys see that go by? Let's see if we can get it up here again. Love spying on the enemy. Where was it? Beacon frame. Right in here. Ta-da! Aruba management packets. It would be fun to copy these and just resend them spuriously and see what happens to their Wi-Fi hotspots. I'm kidding, of course. Okay, so we're going to look for clear to send and request to send. So first let's go down to the requests. And I think there's about 25 things per page here. Thought I may have let this run too long. There's a lot of stuff here. Okay, so let's say it's 25 a page. So what I'm going to do is I'm going to click and just scroll through page by page and count. Page 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 30, 1, 2, 3, 4, 5, 6, 7, 8, 9, 40, 1, 2, 3, 4, 5, 6, 7, 8, 9, 50, 1, 2, 3, 4, 5, 6, 7, 8, 9, 60, 1, 2, 3, 4, 5, 6, 7, 8, 9, 70, 80, 90, 100. There's a ton of packets that were sent. Right, so that's at least 100, and we're at the 4900s. $150 pages. $200 pages. This is getting old. I may have to recapture. Oh my God, how many are there? So like tons. So let's go up to clear to send. Do you think there'll be more, less, or the same? Less, I hear. Let's do a smaller sample. 1, 2, 3. Stop. Let's see how we do this time. Ha! Try having that many pages this time, jerks. Okay, request to send. We have 1 page. What are you guys doing? What in the hell's going on? 70. Oh, we're running out. 85 pages of request to sends. So I hear one person say there'll be less clear to sends. Anybody think different? Everybody thinks it'll be less? If that was an exam question, you would all answer that the same way? Really? You sure? So whose requests to send can I see? Can you hear everyone? Can you see everyone? Just the ones that are close to you. Whose clear to sends can you see? All of them. So what should be the bigger number? It should be tons bigger than the request to sends. So if we come up here to the clear to sends, so it's a hard question to guess. The nice thing, it's one of those questions, as soon as you hear the answer, it makes perfect sense. It's like, of course, that, like, it sounds obvious. So thank goodness it's one of those. It's not like one where you continue to scratch your head forever. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, 30. How many were there? 85, 40, 50, 60, and we have fewer in here. So what's a possible explanation? In fact, we do have fewer clear to sends. So what's some things that could be happening? There could be other Wi-Fi devices around me talking to other access points. This may be completely overwhelming the Wi-Fi access point, and it is not able to give out as many clear to sends. And I would believe that. That is an enormously large number, like an order of magnitude more than yesterday at the same time. So that could be what's going on. It could be lots of stuff is colliding with the clear to sends and I don't see them, so they don't show up in Wireshark because the network's very busy. I could be busy sending all of my own WebEx packets so much that I don't see half of the other people's clear to sends. I am one of the problems. I'm sending a lot of stuff out of my computer on Wi-Fi. Normally, though, you should see all the CTSs and only some of the RTSs. So when I did this the other 2 days, that's exactly what we saw. So there's something weird going on, like that's a big surprise with networking. There's always something weird going on. Okay, the exam will have another one of these pictures. I may give you a hybrid and ask you, I may give you one where 2 of the devices are in range, but the third one is not, or something like that. So know how to spot and know how to look, know how to answer. I may give you like multiple choice to make it easier and show you 3 pictures and say, okay, and which of the following is the following problem apparent? And you can mark which ones you think it is. So it'll be something fun. It's not going to be something that requires that you learn new leaps and bounds in this. If you follow today, you're absolutely going to kill it. All right? And if you're a little lost, then, practice with the simulator a little bit. I gave you the URLs in there. Play around with it. It'll be hard to answer your own questions. You guys have a chat group. Use it. Take a picture, send it. Ask people questions. Make people work. And if you can't get it, ask me. Because I'll know the answer lots of the time, I think. Okay. Yeah, so the things on the first homework will be at the end where they were math questions. How long does it take to transmit? How big is the network? Just review those questions. I will give you that instruction in writing. I will tell you exactly which question it is. And there's one more that I haven't given you that we're not doing today, but I'll give you over the weekend until Sunday to do. I need you to be able to draw me a wired Ethernet collision diagram accurately. I need to be able to show you graph paper. And so what I'm going to give you is going to be something that's going to look like graph paper pattern. You cannot believe the excitement when I discovered this existed. All these months trying to build something in Excel and then paste it over, and just, good Lord, it was just impossible. So this is definitely the way to go. So what I'm going to do is paste a couple of these in and kind of show you what I have in mind, okay? So I'll give you something that gives you a bunch of graph space, and I'll draw a network on top of it with 4 hosts or 5 hosts, something like that. All right, so I'll give you something that says A, B, C, and D, and the slope will be 1, always. So if you're going to draw a line, it's always going to go, just like this, or the other direction. It'll be slope of 1. And I'm going to tell you, I'm going to number these times and tell you at time 0, B starts sending something. Show me a collision where A receives the first part of B before it receives the collision, or the collision isn't detected by B until at least time 15, or I show you the 2 transmissions and I ask you the very important question, when will the network be available again? That turns out to be a really hard question to answer for students. So I'll practice one with you. So let's say B starts sending something right now. So it's going to go like this, and it's going to go, I didn't exactly line it up, but it's not too bad. So it's going to go like that. All right, I'll be perfect on the exam. And let's say B starts sending something at this time. First of all, can you tell me something like, what's the minimum amount of time that any host must continue to transmit, based just on this, visually? Can you at least give me a minimum amount of time? Like, can the minimum packet size be 3 units of time? Like from here to here to here. Would that work? If that's as big as your packet was, would this network function? What do you depend on a wired Ethernet network for the network to function? It's a CSMA CD network, right? What does CD stand for? Detection. You need to be able to detect the collision. Is there a collision on this diagram? Yes. When will the collision make its way back to B? This one here? That's a real one, right? So that's the actual answer from the Ethernet standard. But on this diagram, the collision's not going to be seen. Maybe this network isn't as long as it could be. Maybe this is like a short example. But it can't be any longer than that, right? But the collision's going to arrive here. Is B still paying attention? Is B going to detect the collision? What do you have to do to detect a collision? You have to be listening, right? So how does Ethernet actually detect a collision? Is it listening for someone else's signal? Yeah. Well, that's an acknowledgement at the end. Here's technically exactly what's going on. Ethernet is listening for its own transmission, just like you do when you talk. If you don't think you're listening to your own transmission when you talk, think about when you put on headphones and somebody tells you, why are you talking so loud? Because you can't hear yourself the same anymore. You are always monitoring yourself. And the only way you know if there's something wrong is if you cannot hear that signal clearly anymore. It has nothing to do with hearing other people's signals. It simply has to do with not hearing your own, the absence of your own. So when this signal arrives that came from D originally, in order for you to detect it, you need to still be listening and transmitting, because the way you're going to detect the collision is by noticing that you can no longer hear clearly what you are sending yourself. If you've stopped sending already, that'll never happen. You have to be still transmitting so that you can notice that whatever it is you're transmitting at this time doesn't match what you think was coming out of your mouth. So it's like somebody's walked up to you and they start talking in your ear, and you lose track of what's going on. You immediately know that it doesn't match what you're saying. But so would, like, losing your voice. You also notice you're not hearing what you're sending then either. Right? So there's other examples. So you've got to keep sending, or you'll never notice that whatever pattern is showing up isn't the one you're sending. You can't hear yourself. So you actually don't try to make out what the other person's doing. It doesn't matter. You're just, because you have no idea what they're sending you. How would you be able to tell whether it's right or not? All you know is what I'm seeing on the wire what I'm putting on the wire? Yes or no? Am I hearing with my ear what I think is coming out of my mouth? That's it. That's as simple as it is. So the minimum packet size is at least this long. So you've got to continue to transmit at least down to here, or you will never notice the collision. Now, you guys are smart. You know you're going to have to actually have a minimum packet size that's bigger than that, because this isn't the worst case scenario. What's the worst case scenario? Yeah, one into the other, right? So A, let's move this over to A and see if that happens. If I start sending from A, then I'm going to have to, the collision's going to happen here instead, right? So that happens at this time here, this time T1. That is after this time T0. Well, great. So the collision happened later guess what? I'm going to find out about it later too. When am I going to find out about this collision at A? All the way down here. Much, much later. So I actually have to keep transmitting all the way down to here. If I don't, I'll never hear what's going on. And that's also not the worst case. It can be worse and worse and worse. For example, what if B doesn't start sending at 0 like A did? What if B waited a while? What if B started sending here? The collision will happen here, and you won't find out about it until off the page. How late can D wait to send and still cause a collision? He can wait until right here, right before my packet shows up. So how long is that? In fact, with A, it can be even further. So let me draw it simply so you guys don't leave here confused. The way to figure this out is to know that if you have two hosts on either end of a network, you will not send a packet once you see the network's busy. So the problem is I'm sending a packet like this. Once it arrives at D, D will not send anything. The problem comes up when he starts sending immediately before it arrives. So close that you would just say it's a rounding error, and he actually did start sending when my packet arrived. Yes, infinitesimally small before, but it's close enough that it's the same. So you will not detect that collision until here. Twice the time it takes to go across this network. Once to go almost all the way across, and then for the collision to happen, and for the corrupted signal to come all the way back. You need to still be listening at this point. You still need to be transmitting something and listening to what you're sending, or you will never notice there's a problem. So that's why when we talk about how long does it takes 2 times the propagation time. You must transmit for twice the propagation time to detect a collision. If you don't, you're going to miss some. It has to, it's got to have a minimum packet size. It will pad it with zeros if it has to, like Ethernet. Ethernet will set a minimum frame size. If you don't have that much data to send, you pad the rest with zeros. You must send a packet at least that size. Every single packet from every host is always at least that size forever and ever. Always for the worst case. So she was reading off a minute ago the amount of time. That specifies like how long the network cable could be as well. So every standard has a maximum cable length and a minimum packet size, or it will not work. You'll stop listening too soon, you'll let the packet go too far, and you stopped, or something like that. So just remember, it's like a human. You're not actually listening for the collision, you are listening to the absence of your own signal. That's how you know something's wrong. It's kind of subtle. It's kind of genius, actually. One guy figured all this out. That's a little intimidating to me. You know? Supposedly on a napkin. And different books have pictures of the napkin. I'm not buying the napkin story. I think he did what everybody does with the napkin at the end of lunch. He threw it in the trash. But you do like this, and it goes in the garbage, right? So I don't know. I've never been a napkin saver in my life. I never leave lunches and come home with the napkin, just in case. Someday it's famous. I've never had that life experience. I don't know about you guys. So anyway, there's supposedly a napkin that has the drawing that he made on it. Probably true. Okay, questions on this? Are you guys nervous about this? I had better give you a problem on this one. You need a practice problem to figure this out. So what I'm going to give you is a problem that says, here's how big the network is, here's your propagation speed, how long does it take for a bit to get from one end to the other, how long do I need to keep listening? Make sure you double it. It's got to get to the end and come back before I'll hear it. So, okay, if I must transmit for that long, how big is that packet? Here's my transmission speed, 5 million bits per second. You just figured out how long you need to listen. Now you can tell me how big the packet is. You know how many bits a second, and for how many seconds, how many bits. You can calculate it. That'll be the problem. All right? And you'll have a practice one to do. That'll count as another homework. All right? So get this one in quickly that we did today, because you'll have another one in a day or so. All right? And then the test will be simpler as a result, I promise. Yes?
The homework, the number 2,
Yeah.
the last question.
Oh, did we not go over it? Oh, so, okay, so this is one where if you let this network run for a long, long time, the question is, do you believe it's fair? Do you believe this random back-off mode? I mean, we saw lots of crazy examples where Station 2 had to wait and wait and wait and wait and wait. I mean, eventually, it's probably going to send its packet, but the other ones have sent a lot more, and he's only sent one. Do you believe that's going to balance out over time? Do you believe over time it will be fair? And that's basically what I'm asking you. If after a certain amount of time, Station 1 has sent M packets, how many would you expect Stations 2 and 3 to have sent? And the answer, somebody said, was also M, the same number. They'll all get a fair use of the network. And unless you have a reason to believe this is inherently unfair, that's a reasonable guess that it will be fair. So you have to think about it. Would we tolerate a protocol that was inherently unfair? Would we build billions of them and put them all over the planet if it sucked for everybody? You know, you never got bandwidth out of it. So, no, they'd get killed off. You have to have faith in the IETF or the IEEE. They would not allow it. They'd change it. So you can make rules. You can administer it differently, but by default, it's going to be fair. Yes? Yeah. Yes. Yep. No, it's 10 to the 6. I had it wrong one time, and I hope I went back and corrected it, but megabits is always a power of 10, never a power of 2. Data sizes are powers of 2. Transmission speeds are always powers of 10. So when you look on the Wikipedia page for megabyte and megabyte and gigabit and kilobit, use the 10s. That's the one network transmissions is based on. That's what you'll get sold by the phone company. That's what will get installed. That's the way network cards work. And it makes sense. You hear numbers like 100 megabits per second, 10 megabits a second, a gigabit. Those are all powers of 10. Yeah, that's a good question. Last year, I had it wrong in the homework problem. So I'm wondering if you saw that somewhere. Or now I'm nervous that I had it in the homework. It's always power of 10. And it'll be simple. Okay, questions, guys? We filled the day today, didn't we? We went all the way to the end. I was counting on you bringing back a burger from Food Box. And he guessed right. He said you were going to bring back like a snack from Moxo or something. So you got it right. Yeah. I'll put it in Blackboard with a due date of Friday so you guys can upload it. And I'll publish the solutions after that. You will not need the solutions, you already have them. I think you guys did it right. I didn't get real nervous until the very end. This one makes me nervous. Makes me think I didn't cover it with you or something. I missed it. You know, I'm always paranoid that I leave something out. Now I think I left this out or something. So we'll have to make sure the problem is very clear. And if you guys bomb that question, then that's my fault. I'll give you the points. If I didn't teach you, then that's my fault, not your fault. Okay, we good? Is it going to get cold here this weekend? I'm going back into like 8-degree weather in Houston, so on Friday. Okay, it's always the same, isn't it? I can't escape. How cold? Oh, that's not too bad. Okay. Okay, that's not awful. Could be worse. Could be raining. Okay, I have one more chat message, it looks like. We have doubts about the last question on home. You can talk to me tomorrow. I will be done with my morning class at 10 a.m. and I will remain in my office until 11. How about that? And you can also text me at any time. Okay? Rosa Maria. Bye, guys.